Thank you, Gerard, for the presentation. I bet you can present yourself better than me. I can just say that you are a deep sea lover, not only with ROVs, also deep sea diving. And today you will give a presentation about docking and autonomous control and inspection capabilities. So thank you, and please go ahead.
Okay, so you can all hear me okay, yeah? Yeah, okay, that's great. Thanks very much for the introduction. So a quick look at our research centre. So we are based in the south of Ireland in University of Limerick. Our centre is Centre for Robotics and Intelligent Systems. We're a range of engineers, from aeronautical engineers down to robotic engineers, electronic engineers, and whatnot. We started really in the development of ROV systems. So our first ROV that was designed and built in University of Limerick is this one here. It's the center screen, which is Lattice, we call it. This was an inspection class ROV, which had a depth rating of 1,000 meters. So our center mixes between ROV development, which is underwater robotics, to long-range aerial drone development, and to recently, which is industrial robotic systems. We generally have about 12 PhDs, about 6 or 7 postdocs, and 3 to 4 academic staff. We also recently got awarded a infrastructure grant to purchase a world-class ROV system that you can see here on the left. And I guess the focus of this presentation is the acquisition of that system and the exchange of the software systems that we have developed over the past number of years, and integration of those systems onto this commercial off-the-shelf vehicle, and then utilization of that vehicle in the field. We also have collaborations with port companies in Ireland, and this commercial ROV venture is based on the docks here, which is in the city centre of our town, which is Limerick. So a quick introduction to myself. I completed a PhD in fibre optic sensor systems, and after that really moved into robotic systems and control. The sensor systems and the experience from that was brought into the robotics. And a lot of my research is now looking at the perception systems for ROVs and perception systems for UAV systems. I was a research fellow from 2014 to the present time, and I also do lecturing in controls, circuit analysis, pneumatics, robotics, and sensors and actuators. As Jose referred to, in my private enterprises, I also do deep water exploration. So I'm a closed circuit rebreather diver for Trimix, and in my private times I go off exploring and finding new shipwrecks up to about 150 meters of water depth. So there's a lot of cross linkages between my research area and then some of this exploration in deep water shipwreck. So if we look at the research centre that we're based in the University of Limerick, and the resources and the direction and funding for marine developments in Ireland at present, there is a lot of focus of marine renewable energy, and there is a lot of focus of the resources of our coastline. So Ireland has quite a significant amount of resources in terms of wave action and whatnot, and also wind speed off our coast. You can see the red area here. We're right in the transatlantic wind streams here. So we get quite a significant amount of wave and wind action off our coast. This is being developed through government funding and also European funding to look and get resources from this in terms of energy production, and also to reduce the amount of CO2 that we're producing in the country. If we look at the development and deployment of these MRE systems, If we look at the UK, which is leading the offshore wind, they are moving to, I think it's 30% production from offshore wind by 2030. And Ireland are also looking at significant offshore wind capacities in the next 5 to 10 years. The current ROV systems that are in use in the UK and other areas were developed traditionally for oil and gas, and they are only recently making a transition to have more capacities for offshore wind and other kind of shallow water operations. Your typical ROV system that was developed for oil and gas is this. So you have ROV pilots, generally 2, which are operating the ROV via video feedback and joystick control. So there's mainly manual control of this work-class vehicle, which can be 2 to 3 tons and can be many thousands of meters away from the operator. However, when we move this to shallow water ops, we have to, say below 100 meters, we have to make compensation for both wave action and increased current action. So a traditional ROV that you're looking at here his maximum operation window will be up to maybe 2 meters of wave action and 2 meters or 1 meter per second of current, so 2 knots of current. This has significant limitations for the operations of the vehicle in commercial ventures. If we look at the navigation and accuracy of these systems, these are such images trying to get a world-class ROV to drive straight. So in terms of being able to operate these systems in significant current and significant wave, they're not really suited to that environment. And a significant dependence is put on the pilot skill to be able to operate in shallow water. If we look at this mechanism or the commercial world for this, there is a significant demand really to move these systems from fully manual mode to either semi-autonomous or fully autonomous systems. And what we looked at in University of Limerick is back in say 2005, we developed our own ROV that was based on semi and full autonomy. What we did is we took a traditional system such as this is an inspection class system that we built in UL, and we placed off-the-shelf commercial systems such as INS, DVL systems, USBL systems, to allow us to have significant accuracy in navigation subsea. So what this system does is it takes the last known GPS coordinate frame before it dives. It then calculates its trajectory based on dead reckoning from the inertial navigation system, aided by the DVL system and also aided by the USBL system. In this mode, we can get almost down to maybe 2 to 3 centimeter accuracy in navigation. We can then utilize that GPS coordinate and navigation frame in our autonomy and in our waypoint following for the ROV. So what we get is very accurate waypoint following, go to GPS control, and a variety of different other modes. This is the control system that we developed. We call this OceanRINGS. And you can see we have controllers for heading, course, depth, altitude, and we can also do waypoint following. We can do smart modes where we also follow the ship. Say we have a GPS trajectory from the ship. We can do smart modes where we have a lever arm to the ship, and we can have either the ship follow the ROV or the ROV follow the ship. So look at this. You can see the ROV is just doing station keeping here, but you can see the capability of the system for this. So this is really what we developed over the first number of years in the University of Limerick. This is another example of ship following. So you can see the ROV here. We're doing long transects for multi-beam operations. We're imaging a shipwreck at 170 meters, and we're just doing our waypoint following reading. But it becomes difficult when the area that you're trying to image is over, say, 200 meters long. So to be able to do that operation from a DP vessel, the best mode is to have the ship follow the ROV, or the ROV follow the ship. In this instance, we had the ROV follow the ship 50-meter distance from the bridge section. This is the live multi-beam image coming through here. So you can see this is the trajectory of the ROV. The ship is just over here, 50 meters distance, and the ROV is at, I think it was at 120 meters. The vessel itself here, this is the Empress of Britain. It's the largest ship ever sunk by a U-boat. I think it's 220 meters long or something. It's a couple of feet shorter of the Titanic. But you can see, to be able to do long transects and waypoint following on this is not, it's not a traditional mode of operation, and it's quite difficult for an ROV operation. For this, we simply input for the ROV to follow the ship, and then we ask the DP vessel operator to move the vessel at a specific speed. The mode of operation then for the ROV was more or less in fully autonomous mode. This is the live multi-beam coming in. So this is a Reason 7125 multi-beam, and this is post-process. So you can see the ship is torpedoed at the stern and it's broken hull here. So this is what we had in our university maybe about 7 years ago. So we developed this control system, which was known as OceanRINGS. And what we were doing is smart mode absolute positioning from Finn's INS. What we looked at then is to try and develop this further into perception systems. So have the ROV be more autonomous in understanding its environment and reacting to its environment. We looked at this for both intervention and also inspection. And what we were targeting really was the upcoming resident ROV field, or that's really what it turned into over the last number of years. So there is a push within the industry to allow for permanent installations of ROVs, which are then controlled from a shoreline control and command station. And the target of this enterprise within the commercial world is really to expand the operation of weather windows. If you think about the ROV commercial sector that we talked about a few minutes back, an ROV pilot is pulling the ROV out of the water when it gets above really 1.8 meters of swell, and when it gets close to the 2 knots current window. So this limits quite a lot of the operation of weather windows for both the UK and Ireland, as I think that states about 80 to 90% of our weather windows are above those extents. So if you're trying to operate an ROV, a world-class ROV, from a DP vessel that could cost €100,000 a day, and maybe you're only able to operate for a couple hours a day and a couple of days in the year, your limitation of your operation windows are quite small. Now, if we're deploying quite a lot of offshore wind installations and marine renewable energy installations off our coastline, it becomes difficult, and you need quite a significant fleet of vessels and ROVs to be able to maintain and inspect and keep these offshore installations operational. So there is a drive within the commercial sector to move to permanent installations, which are these resident ROVs. However, there are limitations to the resident ROVs, because when you move to resident ROVs, you need that perception. You need the vehicle to be able to understand its environment. We do have communications, but we do also have lags in communication standards. So if you're trying to do an intervention operation, you could have a 1 to 2 second lag, and that makes it very difficult for the pilot to be able to operate in that. Some of the tasks that this can be troublesome for is, say, when you're docking or exiting the garage. So you can see here, this is the ROV, and this is the garage for the ROV underwater. So when you're entering and exiting this in significant swell or in significant current, you need very high skill for the pilot, but you also need a very dynamic system. So if you have 1 to 2 seconds of lag within your communication system, this makes it difficult for the pilot to be able to overcome that. Other areas such as interventions, so doing manipulation tasks as well. You need a dynamic system that has low lag within the communication. And you also need a very skilled pilot. So what we're looking at in the university is to expand this into semi-autonomous systems where you could have the ROV dock itself, or you can have the ROV grab the plug or do the manipulation fully autonomously. So the different modes that we looked at for our ROV systems in UL was autonomous control in the ROV, which we had done through OceanRINGS, in the manipulation systems, and also in the docking systems. There is other overlaps within imaging systems and coverage. If we're doing an inspection job, it's difficult to understand whether we have fully inspected the site that we came to inspect. So if we're developing a point cloud image through photogrammetry, it's difficult to understand if we've done full coverage of the site. So we develop systems to try and handle that and do quality analysis during the inspection period. So this is the autonomous manipulation system we developed. So what we done when we looked at the manipulated systems that are in the oil and gas and offshore wind sectors, and we realized that about 80 to 90% of manipulators that are out there are utilizing shilling manipulators, such as shilling Titan 4 arms or shilling Orion arms. So we looked at developing a control system, an autonomous control system, which can be deployed on shilling robotic arms. Our reasoning behind this was that if we are to be representative of the commercial world, we need to be able to have an autonomous software control system that can be utilized on the current fleet that are out there. It's difficult to justify developing an autonomous control system that can only be used on a small number of, or a specific subset of manipulator arms. So this is the control system we developed. And we developed an inverse kinematic control for this. And we developed Cartesian space control for the system. And we also deployed a camera system onto the arms so that we could do fully autonomous control. So the camera system gave us pose estimation to the target, and then we utilized that in the control to be able to either turn a target, remove a target, or just insert a target. So a quick example of this. So this is the Cartesian space control. So this is a 7-joint arm, and this is an Orion arm. So it's an Orion 7F, I think. So as you can see, we can move the arm in Cartesian space. So we can move an XYZ Cartesian. And this is done through the control software that we developed. The initial developments of this was done for underwater welding and cutting. So we were looking at very high accuracy of end effector control and pose control for the end effector. So another system we looked at was live SLAM systems and reconstructions. So these are some of the SLAM systems that we developed. So this one is based on feature identification and extraction, and then stitching the frames together to get a photogrammetric model. We developed this further into 3D based systems. So we looked at sparse 3D reconstruction, and we also looked at dense 3D reconstruction, which I'll show you later on. But these are the sort of developments we had initially. But as you can see, many of these developments cannot be deployed on the lattice ROV system that we currently have. So we applied to the Science Foundation Ireland to look for funding for a large work class system. We managed to get funding for it was in the order of about 2 million grant for a full light work class ROV. So this will be the second work class ROV system, which will be based in Ireland. The first one being the Holland one, which is in Marine Institute. And as part of the grant, we also offer this out through access charges, and we often do joint science missions with the Marine Institute with this ROV system. So when we got awarded the grant, we had to go to tendering, and there really was 4 sort of competitive systems that we were looking at, or that applied into the tender. This would be the SMD Atom, which is a hydraulic system. The Forum Comanche system, which is onboard hydraulics, but it's mainly an electric system. And a similar system, which is the CI, SAB CI Leopard. We also had the Ocean Modules V8, which is quite a lot smaller than the other 3. At the end of the tendering system, the selection was the Comanche. So this is from Forum, and it's originally a sub-Atlantic ROV system. So this is the system that we ended up with at the end of the tendering stages. So you can see we managed to get funding for a TMS system, the ROV, the control cabin, and a free-swimming winch. This gave us 2 different modes of operation. We had full depth operation to 2,000 meters through the TMS. And this mode of operation, you deploy this TMS, tether managing system. So it's effectively a garage. So this is a main umbilical here, which goes to a surface launch and recovery system, a LARS. That launch and recovery system deploys this TMS down to 2,000 meters. And then the ROV here has 400 meters umbilical on this drum here. So we have 400 meters excursion from the TMS. So this gives us quite an envelope of operation down to 2,000 meters in Irish waters or abroad. So we can do both research for the University of Limerick, we can do science missions, and we can do commercial operations as well from the system. The second mode of operation was a free swimming mode. So you can see this is the same ROV in free swimming mode. And what happens here is that we have a small free swimming winch with 400 meters umbilical, which is laid out from the deck of the vessel. And what this allows us to do, the ROV is deployed and recovered from the ship's winch. But what it allows us to do is to be able to operate from small vessels. So if we're targeting offshore wind industry, a lot of the vessels that are currently maintaining these devices offshore in the UK are small offshore wind cats. And we can deploy onto small vessels so that we don't have large ship expense when we're doing some of the commercial work, or also doing some of the research work within University of Limerick. So this is the basic outlay of the ROV itself. The ROV itself weighs about 1.5 tons. The TMS is an additional 1.5 tons. And the launch and recovery system here, which is the blue frame. So this is, we can launch the ROV independent of the ship's crew. So this is about 16 tons. We can do either 2,200 meters of excursion from the LARS system, 500 meters from the free swimming. And we also have the 3 software developments deployed onto the ROV. So as part of the tender, when we went to tender, we specified that we could get access to the thruster control and the manipulator control on board the ROV. So we can deploy our OceanRINGS control software onto the ROV. We can deploy the manipulator control system that we developed, and we can do our advanced navigation suite as well. So we had a FINS INS with an ORTEC DVL on board. For the launch of the system, we said we'd do a demonstration of our autonomous manipulation system. So this is basically when you're launching a ship, you often crack a bottle of champagne off the side of the vessel. But we said we'd get the ROV to open its own bottle of champagne and pour the bottle of champagne over the ROV. So this is done through some of the autonomous manipulation software that we developed. So you can see the cork is being manipulated by the second Orion arm. So it's really, during the launch, we just wanted to give a demonstration of some of the advanced control systems that we could do. And we managed to do this over the first couple of months of receiving the ROV. So it actually looked as if we were getting the ROV to drink the champagne, but it was supposed to be pouring the champagne over the ROV. And then this was our first operations. So this was on a DP vessel. So this is one of the DP vessels that are in Irish waters. This is belonged to Commissioner of Irish Lights. It's called the ILV Grand Whale, and its purpose is to maintain all of the offshore lighthouses and buoys off our coastline. So we applied to get access to the vessel, and they gave us 3 days, which was just outside Galway. So we deployed all of our systems and we managed to get out for a couple of days of operations on a smart bay site, which is just outside the harbour in Galway. So it's in about 40 meters of water. We were meant to be going to deeper sites to about 1,500 meters, but the vessel actually got called in for an emergency. So we got cut short from a 10-day operation down to a 3-day operation. But we managed to do a lot of the testing and development of our systems on board over the 3 days. So this was really the first year of operations for the ROV. So we first commissioned the ROV in May 2018, and we got 3 days outside of Galway to do this commissioning and testing of some of our systems. Over that 3 days, we tested the manipulation system that we developed. We did some multi-beam imaging, and we also tested some of the OceanRINGS navigation and control software. We then did a commercial job on a wind farm off the UK coast. So we brought the equipment over to the UK, and we did a 5-year inspection of a substation and associated assets. This was in about 25 meters of water depth, and we were tasked with cleaning some of the anodes and estimating the degradation of the anodes on the substation, and also estimation of some of the free span of the cables and degradation of the cables itself. Our third operation, which we did with the ROV, was under an EU project. So it was a transnational access under the Marnet 2 project. For this, we did some multi-beam imaging over 5 days. So we had to acquire quite a lot of multi-beam data, as the TNA access was to develop a smart system. So using machine learning to identify the attributes of the sonar that can be automated. So trying to automate the specifications of a traditional sonar using machine learning. The fourth operation we done was off the south coast of Ireland, and this was a JRA operation, so Joint Research System under the EU Marine Robots program. So this was also joined up with University of Ulster and University of Galway. So they were looking at both biological and scientific surveys and also laser imaging survey of some of the sites off the south coast. Additionally, on this fourth cruise, we looked at testing some of our automatic docking systems for the ROV. So if you look at some of these operations, this one is the actual control system that we deployed onto the ROV Attain, which we call the MRE-ROV. And this is doing a shipwreck survey. So this is our waypoint following, utilizing OceanRINGS on the MRE-ROV. And what we're imaging here is a liner in about 200 meters of water depth. So the ROV, I think this was 90 meters water depth. So the ROV is doing its multi-beam at about 55 meters. So what we did first is we did a multi-beam over the shipwreck at about 20 meters water depth. And we realized there was a lot of netting coming off the shipwreck. So we then set our close inspection multi-beam to about 53 or 55 meters. So I think the netting was coming up about 20 meters off the wreck itself. So if we look at that, this is a similar survey on the same shipwreck site. So the site itself was a World War I shipwreck off the south coast. It's in about 90 meters. And after doing the full multi-beam, which is a 3-pass system like this, we then stepped off to the side. So we were 20-meter distance from the shipwreck, and we were angled down about 15 meters towards the shipwreck, looking down at the shipwreck. And what we did is we looked at the shipwreck. We asked OceanRINGS to move along to the left-hand side, keep pointing at the shipwreck. So I'll give you a quick look at that. So this is the multi-beam system, and this is the live throughput on the multi-beam itself. So that's the main gun of the U-boat. So in World War I, they had main guns on the deck. So you can see the control that we can get from OceanRINGS and through the commercial the commercial ROV is quite good. We can keep the speed of the ROV to a minimum, which means the point cloud density that we get from the multi-beam system is quite large. So we get very detailed kind of multi-beam point clouds as a result of that. So this is some of the outputs. So this is the main gun that you saw. This is the submarine. This is a secondary gun here, and the conning tower there. So same vessel, you know. So you can see the detail that we can get from the multi-beam is quite good. This is another system. So this one was done at an altitude of 30 meters, I think. I'll just go back there actually. So this here was a pile of netting at the stern. So that was coming up 20 meters off the vessel itself, which was a significant snag issue for the operations. We also had a lot of netting here at the stern of this vessel. So this is a liner, and we did this at 30 meters altitude over the shipwreck as well. Now this is some of the operations. So this is the bow of the liner. That's the breakage that you saw on the liner and the multi-beam itself. So you can see visibility off the south coast in Ireland is quite poor. You get maximum sort of 5 to 6 or 7 meters. You can see some of the portholes here on the shipwreck. Some pottery there from the kitchen area. So we'll skip past some of this, some ornaments. So I think 6-inch. And this is what some of the scientific lecturers that were on board with us. They wanted to prove that they could find some deep water coral in relatively shallow water off the Irish coast. So up until this, some of the deep water corals were only found maybe in 300 meters plus, but we managed to find it in maybe 120 meters. So this is what they were trying to find, and we did quite a good exploration of the shipwrecks to find this. And what we did then is we took some samples of the coral itself, and then the lecturer was going to have to do some DNA sampling and some comparisons between other samples which were taken in deeper water off the north coast. This is the U-boat that you would have seen the multi-beam for. So that's the escape hatch on the conning tower. You can see quite a bit of netting. Now that netting is stuck to the shipwreck, but on the stern, as I said, there was quite a lot of netting coming up off the stern, free floating. So I guess with the OceanRINGS, when we're controlling in semi-autonomous mode, it gives us the ability to do quite accurate control and navigation of the sub itself, so that we can very quickly put the sub in position hold, and we can do finite movements around the sub to get where we need to be. So that's the main gun. Some of the torpedo tubes on the U-boat. We also did an inspection of the Kinsale gas works. So we did an inspection of a wellhead off the south coast. This was also in about 90 meters water depth. So you can see the position here that we've marked, P4. So that is the wellhead itself. And what we wanted to do was a 360-degree photogrammetric model of the wellhead, and also a laser line scan of the wellhead for comparison. So we did sort of two inspections like this. We did a multi-beam scan. We also did a photogrammetric scan, and we did a laser line scan as well. So we had a laser line system belonged to 2G Robotics. So that gives us a very finite detailed picture of the imagery subsea. So this is the wellhead itself. This is a sonar image of the wellhead. So you can see the resolution of the wellhead through sonar imagery. We can only get down to maybe about 4 centimeters. But for the laser line scan, then you should be able to get down to about 0.5 of a centimeter, 5 millimeters. This is some of the imagery that we acquired for the laser imagery. So you can see the detail you do get from the laser is quite good compared to the sonar. And you get similar detail then for the photogrammetric models. So you can see this is a lobster in here under the rock. This was done in collaboration then with University of Ulster, which were also on the cruise with us. And then what we also wanted to test during these offshore missions was the 3D dense cloud SLAM and reconstruction system. So what this does is we have a 30 frame per second camera. So it's a machine vision camera. And what we do is we analyze frame to frame on a pixel-based level. And we generate a depth map for each of the frames. We do a recognition between the depth maps, between the frames, to recognize the movement in the camera. And then we can utilize this information to create a 3D reconstruction of the system. So this is a dense 3D reconstruction, and this is just a demonstration of it. So as we move the camera around, what we're doing is we're generating that photogrammetric model. This is a live version of what you would see online, so it is lower resolution because we do slightly lower resolution to be able to do it in real time. But what this will allow us to do is, as we're moving around, we're generating the model, but we're also acquiring the high resolution data sets. So we can generate a high resolution 3D model of the system after. but the live system will allow us to understand if we fully covered 100% of the inspection site. And it gives us some quality analysis during the acquisition of the model itself. So these are just some additional models that we have done. So these are just targets in about 20 to 30 meters of depth. And these are all done with the MRE-ROV, with the large work class ROV. We then compared these data sets. So you can see the live 3D dense reconstruction system we call stereo fusion. And then we compared this to photoscan, or which is now called Metashape. So you can see the models, they're slightly lower resolution, but we are acquiring this system in real time, whereas this system will take roughly 24 hours to generate. Sorry now. So you can see that the differences there are quite good. And the resolutions that we can get from the live generations are quite unique. The other system we wanted to test on the MRE-ROV after acquisition was the automatic manipulation system. So this is us using the system in Cartesian space control. So there was a rope in front of the target, so we simply moved the rope to the back. And then this is full autonomous mode. So it's using a fiducial marker to identify pose estimation to the target. And then we're simply telling the ROV a simple one-click command, such as turn target 23 degrees, or remove target, or insert target. The last development that we did over these 4 missions was the automatic docking system. So we have looked at inspection systems, such as laser imaging, multi-beam systems, and also our live 3D reconstruction that we developed in UL. We've looked at the autonomous manipulation system that we developed and then ported over to the work-class ROV. And then the last system that we developed was the autonomous docking system. And what we were looking at here was being able to dock the system in significant wave height so that you can eliminate the need for the manual pilot to be able to manually dock that ROV back into its garage. There are many upcoming uses of this system, such as the ASV ROV integrations. So if you want to be able to have an ASV deploy and recover an ROV, an automatic docking system will allow you to overcome communication lags and to eliminate the dependence on the manual pilot in the field. So this was our developments. We did this back in January 2019. So this is our ROV with TMS system. This is the launch and recovery system, and this is the control cabin. So this is our full outlay for the MRE work class ROV, and the ship that we're operating on is the Celtic Explorer, which is one of the research vessels belong to Marine Institute in Ireland. So this was our overall outlay. The camera system was placed, it's a machine vision camera that we placed at the stern of the ROV. And then we had an outlay of navigational LEDs here, which are placed on the back of the TMS system. So the LEDs are placed at a known distance to each other and in a different orientation. So given any orientation that we're looking at this camera, we can figure out which LED is up north and which is south. So what we do is we do a processing workflow for this to identify the centers of each of the LEDs. So we capture the frame, we do distortion, we do some filtering on the system, we blur the system, and we binarize the image. And then we are able to calculate the centers of each of the light markers. Why we do this workflow is try and eliminate image issues such as having a cable in the center of the screen or having some reflections off the system that can portray some errors in our estimation of the center of each of the LEDs. Once we have known positions for each of the center of the LEDs, we can calculate the relative pose estimation from the ROV to the center of that TMS garage system. So it's this pose information then that we utilize to be able to dock the ROV back into the TMS automatically. So in a dynamic mode, we do have a number of interferences from environmental actions and from the actions of the vessel, the support ship. So if we think about this, we have the ROV itself, which is moved by environmental conditions such as waves and sea currents. We have the vessel itself, which holds the TMS via a taut line. So the ship's movements has direct influence on the TMS movements. So if the ship is moving in the waves, you will see TMS heave. You will also see TMS yaw as you move about. And also the ship's roll will have influences on the TMS itself. We then have a pulling force between the umbilical that carries power and comms from the ROV to the TMS. And we have swing as well from the TMS due to the movements of the vessel itself. So all of these influences combine together to make it difficult for the ROV to automatically dock back into that docking station. So if we look at this first, this is a quick video image and a quick outlay of what we achieved during this mission. So when during the initial instances, we deployed the TMS and it was based onto the seabed. So we kept a loose line between the ship's vessel and the TMS garage. This made it quite easy for the ROV to be able to dock. We could do it slowly, and as we had minimal influences on the TMS itself. We still had the influences on the ROV, which were current and sea state conditions. So, but they are quite easy to overcome compared to the disturbances that you will see on the TMS itself. So the second system, our second set of testing that we did was a dynamic system where you have the ROV, which is tethered in the mid-water column. So the TMS is above the seabed and between the ship itself. And this is your typical mode of operation that you will see within the commercial sector or upcoming commercial sector. So this vessel here could be either a small offshore vessel or it could be an ESV. So we have all of these disturbances that we have to overcome for the dynamic system. So you can see this was done in about, it was about 1 meter wave height. So that was about 1.8 meter in total disturbances. So you can see it is quite difficult for the ROV to dock. And what we did for this instance is we took the approach that an ROV pilot will take. So an ROV pilot will line the ROV up in front of the TMS, and at one stage he will commit to docking that system. So what he will do is he'll commit down back into the docking system, and he will make contact with the docking system itself, the docking station. Once he's made contact, he will keep contact with the docking station and make slow movements then to get into the dock itself. So you have to be much more dynamic in this instance and much more committed to the dock itself to be able to get the system in. So you can see, try and make contact with the docking station, and then you make some small adjustments then to get the system into the dock. So these are some of the pose errors that the pose estimations that we achieved during some of the docking. So this would have been the dynamic docking. So it's the third one that you would have seen. And this is the depth error, or the depth estimation on the pose. You can see there is some error here. This should have been here somewhere. So we do have errors, and we are going to implement some outlier detection and elimination there. This is Z, X, and angle estimations of the pose system. As you can see, there are some errors and outliers that we can eliminate. But you can see as you move, so this is distance in ZD. So as you move closer to the dock itself, so this is number 4 here. So you've achieved dock at this point, but as you move, this is your pose estimation as you're getting close. So this is XD and this is angle. Another thing that we looked at when we were looking at this, so we thought about the resident field itself, and we said for resident ROV systems, a typical ROV in absolute control or in dead reckoning navigation estimation will have an INS system on board, which is aided by a depth sensor, sound velocity probe sometimes, and also a Doppler velocity log. Now, what they will do for multi-beam, so if you want to acquire multi-beam and have very accurate estimations, or if you want to do kind of close quarter inspections or interventions autonomously, you have to have very precise navigation and control. Your typical ROV with fins on board and DVL on board will still have significant errors. So you have a drift which incrementally increases over time. And to eliminate this drift, you put in either an LBL system or a USBL system. Now, this makes the overall solution quite expensive. Your fins and DVL will be upwards of 150,000, while your USBL system will be an additional 150,000. So your navigation solution is coming in quite expensive. So we thought to, and also with your LBL or USBL system, there is a significant amount of maintenance for that system. Fins system with DVL will work quite a long time, but a USBL and LBL will require maintenance and ongoing maintenance as they're deployed. So if you have a resident field with all of these systems in place, it can be quite expensive. A lower cost solution might be a Geotag. So if you have, say, the LED arrangement that we utilized, which is the pose estimation unit that we utilized for the automatic docking, and if you place, say, a Geotag, which is an array of these LEDs at a fixed known location, you can eliminate this drift over time. So this is what we looked at here. So as you can see, this is the trajectory of the ROV over time. And this is the incremental error over time in the navigation field. So the gray here is the error without being aided by LBL or Geotag in this instance. And then what we've done is at this point here, we've estimated that we've recognized the pose in a Geotag, and then we can reduce this drift in the INS calculation back down to 0, and we can start our estimation once again. So if you have multiple Geotags in your resident field, so the LEDs, the brightness of the LEDs can still deteriorate, because what we're doing is we're estimating the centers of the LEDs. So your LED Geotag can be in operation for quite a long time, but you could use these to reduce your errors, say once you're coming to do an intervention. So if you have a Geotag next to a number of valves, you could come in and roughly know where you are based on your INS, get your pose information from the geotag, and then reduce your drift back down to zero effectively. This allows you to be very accurate in your navigation. So this is just a small concept that we were also working with once we were doing some of the autonomous navigation systems and the autonomous docking. So that is effectively the presentation. I hope you got some insight into some of the developments that we have ongoing within the University of Limerick and some of the ROV inspection and intervention capabilities that we've ongoing and that we've done in the past. I guess it's back over to Jose and to see if we have any questions.
Yes. Thank you, Gerard.
Yeah.
So let me check if there are any questions in the room. Maybe Jose also has some from the live sessions. I have a couple of questions. So let me just regarding the camera, the computer vision camera that you are using. Is it a stereoscopic camera? What does it use to calculate the depth? Can you tell us more information about the camera?
For the docking system, it's a single, but for the live photogrammetry and the sound system, it's a stereoscopic.
Okay, so it's just light image, no.
Yeah, for the docking system, it's just LED-based pose estimation. However, for the live structure from motion system, it is a dual camera to be able to get that depth estimation.
And then the other question is about biofouling. Any system to control that, for instance, in the geotags or even in the.
So I guess, you know, like if you look at kind of you know, pose estimation systems, if you've deployed sort of a fiducial marker on a printed board for even a number of days, you get quite a lot of biofouling, and that's why we were looking at the LED system. You know, because if you deploy an LED system, the degradation in that can be quite significant. It can degrade and degrade and degrade. All we're trying to do is estimate the center of the LED. So long as there's some sort of light coming out of it, we should be able to estimate the center of each of them LEDs. And that's what gives us the pose. So the degradation within the pose estimation for the LEDs can be quite significant. We haven't tested that, but you know, because you would have to put down the system for a number of months, I guess.
There's one coming our way.
So thank you for the presentation. Regarding the autonomous docking, has ever occurred like an error and damaged the vehicle when the ROV is approaching, due to the fact that like when you have a strong currents?
Yeah. So there is, like, for this system, there is a significant risk, like, you know, because I guess you can see it in some of these docks. Some of the previous ones, maybe we docked them maybe about 10 times, you know, we did maybe a day and a half of testing for this system. But like at the start, I think there's a longer part for this one, but the tether here, this is your comms to the system. So all of your power and communications goes through the system. Now, if that bangs off the frame quite significantly, you're going to have a breakage in your fibers. So you're going to have full loss of control to the ROV, basically. And that's quite dangerous for the ROV, because if you do lose control and you're in maybe 1 to 2 meters of swell height, it's going to be very difficult to get the ROV back into the dock. Now, you still will have control over the winch, which is on the TMS, but your comms to the ROV will be gone, you know. So So that is the risk, but I guess that is why we started with the system on the seabed, so that we could see how much risk we're taking on here, you know, and we saw that, you know, through the developments of that and the testing of that, it was quite good in not being so much in air that the middle of the ROV was hitting the frame. So we weren't getting into a position where it was often going to hit the middle of the ROV to the frame, you know. But we also did have a manual pilot ready to take over as well. So.
So can I ask another one?
Yeah.
Regarding the communications, have you since you are using more autonomous behaviors, have you tried having latency or lower bandwidth, and how will it degrade the control?
So we were looking at putting it through some SATCOMs systems. Now we have controlled it over the ship's SATCOM, which is the ship has maybe, I think it's a 1.5 to 2 megabit connection over satellite. And we have controlled it over that, but it will be it's only waypoint following and simple kind of depth hold and different things. We haven't put it in kind of dangerous operations like this per se, you know. So we haven't fully tested it to that extent. We were talking about, you know, going down further into that and testing more of the lag and to see how the system operates within that, you know. But like for the ROV control, we're sending down high level commands all the time. So it's really, it's not like manual commands where you're trying to move out of the way here. But we haven't done manipulation commands, and we haven't done docking commands over satellite. We've done all of the ROV commands itself. So waypoint follow and depth holds, you know, position hold and different things like that.
Thank you. Jose, can you hear me?
Yeah, I have a comment from the attendees in the Zoom webinar. It's from Omnia Ibrahim, and he's saying that creativity is make scientific devices and experiments very interesting and leading to helping a lot of very accurate observations, isn't it? And I will build on this, let's say, comment and ask you for in the future, is foreseeable, like if we could, for example, have these docking stations in the deep sea linked, for example, with submarine cables and non-tethered, I mean, devices could go from one place to the other, or is something that is impossible in the next few years?
I guess, you know, a lot of the developments we're focused on are relevant to that resident offshore fields, you know. So, and I guess that's where that comment is coming from. Like, there is a push within oil and gas to try and move to the resident field and to move to that situation where you can have an ROV which is docked on one wellhead, and it can do all of the inspection and maintenance on one wellhead, and then it can move maybe 2 kilometers to a new wellhead. You know, that's where the industry is moving to. As a research center, we can develop and showcase some of the parts of that, but like we don't have the current funding. Our projects are you know, large commercial projects that an oil and gas project will have, you know, to be able to showcase and demonstrate that. But the battery systems, there are new systems that are out there that will allow the capacity to be able to move between wellheads and to be able to dock. I think the connection systems, say there is wireless connection systems that are on board. The power and the comms bandwidth are fairly low for them at the moment. But I mean, like these systems are developing all the time. You are seeing optical modem systems that have high bandwidth. You are seeing wireless charging systems that are coming on stream. So, you know, this is where the oil and gas industry is moving, and there's significant money behind it to make it move this way. But I do think it's still quite a good number of years off before you're going to see full systems like that in operation, you know.
Okay, thank you.
So I think in the classroom we are done with questions. If there aren't any other questions.
Not on my side for the moment.
So thank you, Gerard, again for the presentation, and I hope we can see next without the masks sometime soon.
Yeah, thanks very much. That was it.
Bye bye.
Thank you so much, Gerard.
See you now. Bye bye.
Okay, bye, bye.